Morning. How's it going? It's Wednesday morning, week 2 of our virtual lessons. How's it going? Can you hear me now? Are we awake and on? Good morning, Destiny. Morning. I have my early bird up. I'm ready to go. Oh, I didn't draw a little bird. Let me draw the little bird. My little early bird. Although I didn't start too early. Here's my little early bird. There's your early bird. Howdy, Aunt Kara. We got Destiny and Kara. The rest of y'all, come on, join us on this April Fool's Day. April 1st. April Fools. I feel like this is an April Fool's year. Not just a day. It's been going on for a couple of years now. April Fools indeed. Get a couple of other people in here this morning. Morning. I'm awake. You awake? Kind of, sort of, anyway. Slightly. Hey, there's a few more joining us. Walking into class. There's Zoe. Yay! Who else is here? Y'all be sure to let me know you're here once you get here. And then y'all can start thinking about this. Early bird. There's Adam. And Alyssa. And Bo. Jasmine. Woot. Good morning. How's it going? Getting a full class in here. Perfect. 4 prisoners must draw from the urn without replacement. The guards execute the prisoners who draw a green ball. What is the probability that only one prisoner is executed? Hey Eve, good morning. And then our haiku this morning. Expecting a joke? I've got one for you. What did... Oh, wait, no, I'm out of... On this April Fool's year. Day. 3 years. Whatever it is. Seems like April Fool's for a long time though. I won't do April Fool's with you. It's already too much going on. I won't be mean today. Too much. So, how about we get it going? Looks like we got a full crew. We'll get going this morning. So, today we're going to talk about hypergeometric distribution. Yesterday we did binomial, and today we're going to do hypergeometric, and then tomorrow I'll do the task for you like I did last Thursday. Morning, Kelsey. And then next week we're going to talk about expected value. So we'll move into expected value next week. So I don't know if I gave y'all a revised schedule or not, but that was not on the revised schedule for next week. But I'm revising the revised schedule, so it's going to be expected value next week. We're playing it by ear. Hey, Priscilla. Now here's the question, can I use binomial on this? We did binomial yesterday. Can I use the binomial distribution on that? Are you trying to use binomial on that? Can I use binomial? Why or why not? Why or why not? If you say yes, tell me why. Not binomial like expected value destiny, but expected value with all probability. So we looked at the expected value for just binomial. That was nice and easy. But we're going to look at expected value for all probability next week. There are two outcomes, death and not death. I like the death and not death. What else? What are the other conditions? That's condition number one. Why or why not? If you say yes, you're giving me that. If you say no, tell me why not. Adam, I'm talking to you. You got death and not death, live or die. What else? What are the other conditions of binomial? A fixed amount or set amount of experiments. Is there a set amount of experiments? Yeah, we're going to pull 4. But Adam says, look at that probability. Is the probability remaining the same? So y'all told me that it has to remain the same, and is it going to remain the same? So to take a green ball out on the first one, it's going to be 1, 2, 3, 4, 5 out of 8. But once I take a ball out, does that probability remain the same? Yeah, so I cannot use binomial because the probability does not remain the same. So that was fun and all. If you were trying to use binomial to solve this, we got to look to see every time if it meets those 3 conditions. And this particular one doesn't meet those 3 conditions. So we go back to that classical idea, back to, well, how many different ways can I do it? What do I have to do to get it? So let's go back and use our, last week's stuff where we're just coming up with all the different ways. And then maybe I'll give you an easier way afterwards. I don't know if it's easy or not, but we'll use hypergeometric afterwards. By the way, while I'm thinking about it, yesterday I know y'all did your homework. You guys finished it up with me online, but I only had 2 people turn in the homework. Only 2. What's up with that? Y'all finished it. Go ahead and upload it. Now, out of those 2, one of them, if you're one of the 2 that turned it in, one of them I know finished the homework but uploaded only half of it. That's why I want you to go ahead and upload it, is because you might do something where you miss uploading all of it. So if you're one of the 2 that turned it in, check to see. I graded it, and if you're the one that you didn't turn everything in, I said, hey, turn it in by Saturday. So it gives you that opportunity to turn it back in. And for the rest of y'all, turn it in. That way, if you make some little mistake, like not everything got uploaded, I can correct it and fix it. Go in and check. If you're one of the 2 that turned it in, y'all check to see what your grade was, see if you got it all uploaded right. See what my comments were for you. Okay, fine. I'll be on again today so we can finish it up. Okay, there's my motivation for the day. All right, so back to this. Now let's figure out. We have 4 prisoners who are going to draw from the urn without replacement. The guards execute the prisoners who draw a green ball. What's the probability that only 1 prisoner is executed? So now we got to come up with the different ways. So one way that only 1 could. Good, Priscilla. That's exactly right. Because we're going to have this guy could get a green, and then or live. You could do it die and live or whatever. Green, not green. And not green, and not green. So it could be the first one, or that green could go in the second place with the not greens around it, or the green could go in the third place, or the fourth guy who draws it could be the one that died. So you're exactly right. There are 4 different ways to do it. So once we know how many different ways there are, then it's just a matter of finding the probabilities. Because we saw that when we did all our tasks last week. So here, the probability I get a green on the first one what is that probability I get a green on the first one? I can't seem to not just leave it. I have to write it out. I like it. So this one is, well, there's 5 out of 8. And then not green, well, there's 3 out of 7. And then once I take out a green, there's only 7 left. But there's three nots. Then after I take that one out, now there's only 6 and 2 nots. And then once I take that one out, then there's only 1 knot and 5 left. Now let's just check to make sure that the probability does remain the same. We think it does, but let's just make sure. So if I do not green on the first one, well, that's 3 out of 8. And I take that out, well then green on the second one would be 1, 2, 3, 4, 5 out of only 7. So now I've got those 2. Now there's 2 not greens out of 6. And then there's 1 out of 5. Notice that while these guys are different, the numerators are the same. And my denominators are the same. So it's going to turn out to be the same every single time. So even though it's in a different order each time, this one's going to be 3 out of 8 and then 2 out of 7 and then the 5 out of 6. Because I'm taking 1 out each time, my denominators just go down by 1. And then I'm still going to have 3, 2, 1 for my not greens once I take 1 out. And that green is going to be 5 every time. So yes, they stay the same even though they're in a different order. So I can just take this and multiply it times 4, which y'all have already done it. But I'm going to do it again just to make sure I don't lose anybody. So 3 out of 7, 2 out of 6, and 1 out of 5. Y'all are also getting better about canceling before you multiply. Today that's going to be even more important. It's going to be super important that you guys cancel or simplify as much as you can before you multiply. You're going to see as we work these, that's going to be like extra important on today's. So keep yourself neat and organized. I'm going to show you how to keep it in a linear fashion. Then it's a matter of you doing it as well. Okay, so here, this 5 and that 5. This 3 goes into that 6, or you could do the 2 6 is the same as 1/3. And then this 3 and that 3. And I'm doing that 4 times. So this 4 goes into that 8 twice. And you're right, we just end up with 1/14. That's the probability that someone dies. Just 1 out of 14. How did y'all get 1 out of 14 times? Did I leave something off? Because I used the 4 already. So it would have been 1 out of 56. But because of the 4, then it's 1 out of 14. Did I do that wrong? Okay, maybe I got it. So it's 1 out of 14 chance that a prisoner dies. Mr. Simpson, what battle was this that they actually did that? They, Texas-Mexican War, I think, and in some little Texas town where they actually did that. They bring out the prisoners and have them draw, and if they got a black ball, they executed them, and if they didn't, then they got to live for the day. So I'm sure that stress was kind of like the stress of coronavirus. Every time I go out, I'm like, am I going to draw a black ball or not? That's how I'm feeling, except a little bit different maybe. So, okay, so today we're going to see that we can use something called the hypergeometric formula whenever we're dealing with something without replacement. But notice, it may have been, Adam, but notice that we can just do this classically. I mean, we figured it out even without that. And that was the same was true with the binomial. We could just kind of brute force figure it out. But then the formula is there to help us if we need it. And sometimes it does make it a little quicker if we can use it. All right, so let me just give you the formula today for us to use. It's a little more complicated and a little less intuitive than maybe the binomial is. Because on the bottom of our probability, is always the total. And in this case, what we're going to do is we're going to look for the total number of ways that I can pull 4 balls out of that urn. So I want to know first, in the denominator, the total number of ways I can choose whatever the sample size is from my population. So the population choose my sample goes on bottom. And I'm just looking for how many different ways could I choose 4 balls from this 1, 2, 8. How many different ways could I do that? Then on top, in my numerator, I'm going to be looking for whatever the number of successes is that I want. So we're going to have some successes and we're going to have failures here. And you can kind of see the 8, 7, 6, 5. You can see that kind of combination type of thing going on. And since the order is not mattering, that's why we've got a combination there. So first I'm going to look at the total number of successes. So like in this case, my total number of successes is 1, 2, 3, 4, 5. 5 successes. That's the total number of successes. I'm going to use K to talk about the total number of successes. I'll write down these things here in just a second. Let me get them up here. And I'm looking to see, out of those total number of successes, how many am I pulling out? So this is from the whole population. How many different ways can I choose a sample? And up here, these are just the successes. How many total successes do I have, and how many ways are there to pull out, in this case, 1 green? Then I'm going to look at the failures. Well, if there are 8 balls and 5 greens, I can figure out how many whites there are by subtracting. I'm going to take my population and subtract the number of successes. And then I'm going to take my sample and subtract the number of successes I want. So let me make this make more sense. I know right now I'm just kind of putting the formula up there. Hopefully it'll make a little more sense here in a minute. So let me give you what each letter stands for. N, just like always, is our population size. Lowercase n, just like always, is our sample size. The only new variable I've given you here is this K. And the K is going to be the total number of successes. And then your X is the number of successes we want. Okay, so this is going to be my successes, which means this one over here is my failures. So you've got 2 groups every time. Here I'm talking about my greens, and there I'm talking about my whites. And then down here is the total, total, total. So let's look at ours and see if we can figure it out. So from this one, what is my population size? So in this, there right there, what is the population size? In other words, how many total balls are there all together? What's that population size? There's a total of 8 balls. So that's going to be my population size. Good. Then my sample, I'm only going to pull out, how many balls am I going to pull out? I'm going to sample or take out 4 of them. That's my sample size. Then, how many total successes are there? In other words, how many total green balls are there? How many total green balls are there? 1, 2, 3, 4, 5. And then the total, then how many of those green balls am I looking for? How many do I want? Well, I want one of them. So here, I'm going to do A choose 4, and that's going to tell me how many different ways I can choose 4 balls out of there. Good job, guys. And then here, I'm going to have 5 total green balls, and I want to know how can I choose one of those. How many different ways can I choose one of those? So now I'm going to fill that in. So in my denominator every time, I think to myself, I need the total, because that's what goes on the bottom of my probability. Total. So total, number, and then the total I'm pulling out. Then on top, I'm going to think about my successes, or whatever it is I'm looking for. So in this case, greens. The total number of those greens, and how many of those I want. So in this case, my x is 1. Then, so I've got total successes. Then over here, it's those other guys. So how many whites? So look and see what's the total number of whites that I have here. How many total whites do I have there? Good, I have 3 total whites. And if I want one of the greens, and I'm pulling out 4 balls, then how many of those whites do I want? You know, if I'm taking out 4 and I want one to be green, then how many whites would I want? Good, I need 3 of those too. Notice, big deal. Notice this plus that should always equal this. My successes plus the total number of successes plus the total number of failures should always add up to be the total in my population. So these 2 numbers should always add up to be that top number. And this bottom one, the total number of successes I want plus the total number of failures I want should always add up to be that sample size. So this plus that should give me this, and this plus that should give me that. Now that looks really complicated, right? We're going to have to do this combination, and that combination, and this combination. There are 3 different combinations we have to do on this problem. Now, if you looked at that Pascal's triangle, or if you've done enough of these combinations, you'll start to see some patterns within these combinations that will make it easier. So for instance, if you did that bonus from yesterday, that Pascal's bonus from yesterday, maybe even you can look and just know automatically what my 5 choose 1 is going to be. Have y'all figured out this pattern? When I have 1 in my as my bottom number there that I'm choosing, what happens every time? Because there's a pattern to it. So y'all take some time and look at it, because once you start seeing those patterns, it really helps. But let me show you how I'm going to work this out neatly and organized, and I want you to do it this same way. And Eve, I'm talking to you too. So I want y'all to make sure that you're doing it in the same order, same way. Hey, Giselle. So that you can keep your work nice and neat and together. Okay, so watch how I do this. First thing I'm going to do is this first combination. I'm going to put in here so that I have 5 factorial over 1 factorial over 5 minus 1 factorial. Okay, notice it's right here on my fraction. That's where I'm going to put it up there. Then I'm going to do this one. And maybe you've figured out the pattern of every time that it does the same number there. I know Adam has. He's looked at this Pascal's triangle and he's got these patterns down. So maybe you've noticed what that's going to be every single time. But I'm going to go ahead and work it out this time. So this is that combination. Now I'm going to do this combination. So times 3 factorial over 3 factorial times 3 minus 3 factorial. Then in the denominator, I'm going to do that 8 choose 4. So here, 8 factorial over 4 factorial times 8 minus 4 factorial. Okay, now watch. I'm going to keep this together just as it is. So first I'm going to work this out right here on that top left. I'm going to keep it there. Okay, so here I have, well, I'm going to do the bottom first, so 4 factorial, 1 factorial, so I know where to stop here. So do that subtraction first, so you know where to stop. So now on top I can go 5 times 4 factorial and I can stop there. Boom. By the way, every time I subtract 1 from it, it's just going to be 1 less. Whatever this first number is, you know, when I subtract 1, it's just 1 less from that top one. Happens every time. Okay, then here, 3 factorial, I'm going to do the bottom first again. Then 3 factorial, again, this lets me know where to stop. Well, I just stop at 3 factorial. I don't need to do any counting down because there's a 3 factorial there. So anytime the number on top is the same as the number on bottom, you know, when I subtract, I'm going to get 0. So notice what's going to happen here. All right, now, in my denominator, I'm going to do this denominator first. So I've got 4 factorial, and that one, 4 factorial. So I know I need to stop at 4 factorial. 8, 7, 6, 5, 4 factorial. Okay, this 4 factorial and that 4 factorial disappear. They cancel, they simplify to become 1. This 3 factorial, that 3 factorial become 1. This 4 factorial and that 4 factorial become 1. Okay, I'm going to keep it together still. I'm still going to keep this organized. This is going to be the hard part of this today. I mean, it's going to be hard enough to set it up. I probably shouldn't have erased that formula. Oh well. We'll come back to it. I'm keeping it together. So I'm just going to move down my page, and I'm going to keep this on top. Look, what is 5 divided by 1? Oh yeah, that's just going to turn out to be 5. And it turns out every time I'm choosing, you know, that 1 on bottom, it just ends up the pattern. Anytime I'm choosing 1 on bottom, it turns out just to be that top number. So like if I did 7 choose 1, if you look at the Pascal's triangle, it turns out just to be that 7. That's a pattern that's there every time. Okay, and it's because you'll end up canceling out and you're just left with that number, whatever it is on top. Here, 3 factorial divided by 3 factorial made 1. This is just 1, so I'm just left with 1. So the pattern here is when the numbers are the same in there, it just ends up being 1. You're at the end of the Pascal's triangle. So it just ends up being 1. So like 5 choose 5 is just equal to 1. 1,000 choose 1,000 is just equal to 1. When they're the same, it's just equal to 1. All right, so that's equal to 1. Now I'm going to look on bottom. Remember that this is 4 times 3 times 2 times 1. 4 times 3 times 2 times 1. And here I still have 8 times 7 times 6 times 5. I'm going to find some things to simplify. Like for instance, 3 times 2 is equal to 6. So I'm going to simplify this 3 times 2, and that's 6. This 4 goes into that 8 twice. Notice I don't have anything in the denominator. We know that, you know, if I'm just dealing with this, we know from doing combinations I should be able to get down where I don't have anything in the denominator. So now I'm just going to rewrite it again, 5 times 1, and on this denominator I now have 2 times 7 times 5. But you see this 5 and that 5? They become 1, and I'm just left with 1 over 14. Now notice when I worked it out, I kept it together. It's a big, huge, multiple layered fraction that I just kept as a big, huge, multiple layered fraction. That I kept as a big, huge, multiple layered fraction all the way down. And I'm just really careful about when I cancel out, writing it down and making sure that it comes down with it. So I swear today this is going to be your biggest challenge. It's just keeping it all together. Okay, so let's do another example. Let me erase all this and put the formula up there so that we have it. So here's the probability of x. Again, on the bottom is my total. So from my population, what's that sample size I'm choosing? Then on top, it's the total number of successes, and how many of those successes do I want? And then over here, it's the number of failures. And I can, figure out the number of failures. I can also just find that, take your population and subtract the total number of the successes. And then, same thing here. So just a reminder, n is pop size, lowercase n is sample size, although I'm about to cover this up, so I don't know why I'm writing it. This is total success, and this is success we want. And we do always want success. All right, let's do another problem. So, I have them right now for us, ready to go. You can almost see our formula up there. There's a lowercase n down there. All right, so you remember Tiny Tim? We've already done this problem. I'm just going to show you now that it is hypergeometric. By the way, I didn't go through the conditions of hypergeometric, but you notice it's just like binomial. The difference is it's without replacement. So when I have a population and I'm choosing a sample without replacement, I still need those two. The successes and the failures, and I still need a fixed number of trials. It's just that now it's when the probability is changing, so I'm doing it without permission. I mean, without replacement. Without replacement. Now, there we go. There's Tiny Tim. We've done this problem with the classical, and now we're just going to do it with the hypergeometric. So Miss Stash is very organized. My house, too, super organized. But I might have some knives in with the toys. I know right where they are, though. So she keeps her 4 knives with Tiny Tim's 16 toys in the playroom bin. Tiny Tim blindly selects 3 items from the playroom bin without replacement. What's the probability Tiny Tim selects exactly 2 knives? So we've gone through and looked at all this. This is how my house is set up too, just like it. Just don't call CPS on me. My kids are adults now, so it's fine. Okay, so here we go. Let's see. It's still 2 outcomes, knives and toys, fixed number of trials because he's taking out a certain number. And then, but the probability is going to change because we have that without replacement. So now we just have to figure out those 4 letters, or those 4 variables, what are they equal to? So what is the total number of items in my bin? Because that's going to be my n. Good job, y'all are already doing it. What's the sample size? How many am I going to pull out? How many is he going to sample from that total population? How many is he going to do? He's going to select 3. And then Yeah, good. It's the 16 knives plus the 4 toys to make a total of 20. Now notice I didn't just give you the 20 in there. You had to go and figure that out. So really you got to read the question, think about the question first. You know, I want you to think things like, man, Miss Stash is sadistic. I want you to think, man, I need to call CPS on Miss Stash, because you're so much thinking about the scenario and what's happening within it. So that's step number 1 in all of these problems, is you got to figure out first what's going on to be able to think and reason about the question. Hopefully next week, at some point or another, I'm going to start giving you some charts and graphs of the things that we're seeing right now in the real world, especially with this virus happening, where I want you to be able to think and reason the things that are happening so that you can begin to think for yourself. You know, before spring break, when my daughter was in China, we looked first at the death rate of this, or the mortality rate of this virus, and we saw it, and at first we weren't worried about it, but then things started happening, like they were starting to close down roads in Beijing, and as things started happening and it started traveling to other countries, I want you to be able to look at that information without looking at what the people are telling you about it, and begin to make some logical choices on your own. Like, for instance, I was really glad the school shut down, because at the time I was thinking to myself, I don't want to go back to school, or if I do, I'm going to take a thing of wipes and start wiping down in between every class and wiping my hands, because I was already starting to worry about it. While we were in spring break, I was like, this is going to be dangerous. So I want you to be able to reason and think those things, even if other people are telling you things like, it's going to be fine, y'all go on out. I want you to think and be able to think about it on your own. And being able to read a question and think about what's happening in it is part of that critical thinking that we're learning from this. All right, y'all are way ahead of me. So my K is how many knives there are, and there are 4 knives, and you're exactly right, we're choosing 2 of them. So maybe you even have it set up so that we're choosing 2. I always start with the bottom. I go, on the bottom is my total. So how many total things is it? First it's 20 total things, and I'm choosing 3. You're right, Eve, it is. It's affecting everybody. At first we thought it was just older people, but it turns out that anybody can get it, and so because of that, then it's just a matter of how bad, you know. So it is all ages. I don't want to scare anybody. Y'all just stay away from people, all right? Physically distance. And if you're one of those on the front line, just make sure you're washing your hands and not touching your face, doing everything you can. All right. Then on top, so that's my total. On top, it's the total number of those knives and how many I'm selecting. How many ways can I select those 2 knives from those 4? Then, this is always the hardest one, because now I'm looking to see how many are left. So if there were 4 knives, how many of the others are there? Well, it tells us actually in the problem. It tells us that there are 16 and 1. You know, if I'm choosing 2 knives, that means I'm getting 1 toy. If there are 4 knives, that means there are 16 toys. Notice these guys add up to be that, and these guys add up to be that. Still skewed, that is true. It's still skewed towards the older people, but there is risk to the younger people after all. So. This is exactly this statistics class with what's happening right now. There's so much going on that, like, I'm almost overwhelmed as a teacher, because there's so much I want you to see and listen to. I listen to that. I've told you about it before, called The Daily in the Morning, the podcast. And every morning I'm like, man, I wish my students would listen to this, because then all of a sudden, all the statistics, they would start hearing some of the words that we've been talking about. So there's just so much out there that if you understand statistics right now, it helps to analyze this information that they're giving you. Hopefully you're being able to use some of your stats with the news that's going on. Okay, now this is the tricky part of this whole thing, is keeping this organized and together. So, I'm going to do that. 4 factorial over 4 minus 2 factorial over 2 factorial times 16 factorial over 16 minus 1 factorial over 1 factorial. Then, I've got 20 factorial over 20 minus 3 factorial over 3 factorial. And again, I'm going to keep it all as a big fraction. Don't do this piece. I know what y'all are going to do. I've seen your papers. You're going to take this piece and try to do it over there. You're going to take this piece and do it over there. You're going to take this piece and do it over there, and then try to put it all together. Don't do that. Keep it nice and organized, please, for me and for you. It'll make things easier. Okay, so now, this is a 2 factorial on bottom, 2 factorial. On top, 4 factorial times 16 minus 1. By the way, don't we know what this is supposed to be? Didn't we just do this a minute ago? If I have 16, choose 1, what's that going to be? What was the pattern that we just figured out? I shouldn't have to go through this process anymore. So 20 minus 3 is 17. Okay, by doing that subtraction for each one of them first, now I can see where to stop. So now, I'm going to stop this one at 2. So 4 times 3 times 2. 2 factorial, 2 factorial. These guys are going to go away. Now I know where to stop. 16 times 15. That becomes 1. Then, I'm going to stop at 17. So 20 times 19 times 18 times 17. I'm going to go ahead and count this down. 3 times 2 times 1. And next one I'll do colors better. Yeah, that's exactly right, Jasmine. 16, choose 1. It's just going to be 16. Every time I'm choosing 1, it's whatever that top number is. So here, I'm going to keep it together now. This 2 goes into that 4 2 times. So this fraction, all I have left of it is 2 times 3. By the way, you're just going to keep going down your page. So it may take 1 page per problem. Be nice and neat and organized about it. It's okay. I have two trees out on my front porch that I need to plant today. I'll show you those trees. I don't know, I might plant them today. But maybe if I don't get around to planting them, I'll show you. I'm planting trees every day to make up for the paper that you're using. Here's 16. So it's okay to use some paper. I plant trees. Then here, let's do some canceling. Well, 3 times 2 is 6. 6 goes into that 18 3 times. So now here's where it gets, I need to make sure I write down everything. 20 times 19 times 3. 20 times 19 times 3. That's me. I'm a tree killer. I'll hug them and then kill them. Okay, so just know that about me. I'm going to hug you and then no. So here we're going to do some simplification. Notice again how if we multiply everything out first, it's going to make this really hard. So that's why we've been building up to this being able to simplify as we go along. Just makes things easier. So this 3 and that 3 become 1. I don't know, how about this 2 goes into 20 10 times? But then I see that this 16 and that 10 both have a 2 in them. So I can make this be 8 and this be 5. So now I'm just left with 8 over 5 times 19, which is 45 carried to 4, so 95. So 8 over 95 times, 8 out of the 95 times he reaches in, he's going to end up with 1/9. All right, how was that? That feel any better? Feel okay? Let's do another example. All right. A batch of 10 rocker covers. Oh, a batch of 10 rocker cover gaskets. So whatever a rocker cover gasket is. Rocker cover gasket. Huh. 2 times 3 and then 16. And then on bottom, 20 times 19 times 3. I didn't leave something off, did I? So that 2 and that 20 become 10. That 3 and that 3. That 8 and that 10 becomes 5. So I got 8 over 95. Okay, we got it fixed. Okay, good. Let's do it again. Yeah, let's definitely do it again. So Jasmine, you haven't been in my class to watch me do this all semester, where we're going to simplify before we finally get around to multiplying. It just makes it a little bit easier. But the tricky part of this is keeping up with everything. So y'all have got to be neat. There's a couple of y'all specifically I'm talking to. You've got to be neat and organized. Rocker is the engine part. Glad to know that. So we got 10 rocker cover gaskets, and they contain 4 defective gaskets. So 4 out of the 10. Oh man. An inspector chooses 3 gaskets to inspect. You know, they don't have time to inspect every single one of them. So they're just going to choose 3 of them. I want to know what's the probability that the sample contains 2 defective gaskets. So when he looks at it, what's the probability he gets 2 of them that are defective? Okay, so picture again what's happening. You've got this inspector. He's got a whole bunch, 10 of these gaskets. He's going to randomly choose some, look at them, and see if they're defective or not. So the first thing you want to do is picture what's happening. Adam says shut down that line. They need to do something about quality assurance. All right, so what is my population? What is my in that case? Yeah, when we do some simplification, we might end up with a little bit different, Bo, because I may have canceled out the 10 and you did the 16 or something. So that does happen sometimes. Good. My total number is 10. And then I'm choosing out of those 3. Perfect. Now, how many successes are there? How many successes am I going to have from that? How many total successes? And in this case, what is a success? So I'm looking at the defective gaskets. So in this case, my successes are defective gaskets. How weird. So I have a total of 4 good of those defective gaskets. And I'm getting 2 of them. I mean, really, we could call those the failures and then the not ones successes. It doesn't really matter, except we're looking for gaskets. That's the only thing that makes them the successes. Okay, now I'm just going to plug it in. And now it's just a matter of doing the arithmetic and keeping it. So I always start with the bottom, 10. The total. I always think to myself, in probability, the total goes on the bottom. The total number of outcomes goes on the bottom. Then on top, it's what I'm looking for. Well, I want my successes. So out of those 4, how many different ways can I choose 2? Then, if there are 4 defective, then how many effective, how many working gaskets are there? So, you know, if there are 10 total and 4 of them are defective, that means that there are 6 that are actually working. And then, good. And then, how many of them am I going to choose? You know, if I choose 2 defective and I'm looking at, I got 3 in my hand, and 2 of them are defective, then how many must be working? Then there's 1 that's working. Again, notice these 2 add up to that, and these 2 add up to that. All right, now let's just do the math. Keep it together. See if you can keep it together. 4 factorial over 2 factorial over 4 minus 2 factorial. Times. Oh, you already know what this one is. 6 choose 1. What's 6 choose 1 going to equal? I don't even have to write out the factorial anymore. I know what it's going to be. What is 6 choose 1 going to equal? Just 6. Anytime I'm choosing 1, it's just that top number. So once you start seeing some of the patterns, it really helps. So maybe look at that Pascal's triangle and help you see some of those patterns in there. Then 10 choose 3. Okay, I'll go ahead and write that one out. 10 minus 3 factorial over 3 factorial. All right, I'm going to stop this one at 2. So 4 times 3 times 2 factorial. I already know that one's 6. Leave him alone. On bottom here, I'm going to end up with 7 factorial. So I know to stop this at 7. 10 times 9 times 8 times 7 factorial. I'm going to go ahead and count down this 3 factorial as 3 times 2 times 1. Don't forget to count him down. So that's 7 and that's 7. This 2 goes into that 4. Oh, I was going to use a different color. I forgot. Goes into 2. I even got out my different colors to use, and then I didn't do it. Let's see. This 3 goes into that 9 3 times. And this 2 goes into that 8 4 times. So here, all I have left is 2 times 3 times 6. Notice, I am still not multiplying those out. I know that 2 times 3 is 6, but I did not multiply it out yet. I'm going to wait till the very end to multiply it. Then here, all I have is 10 times 3 times 4. Now I can still simplify this 3 and that 3. 2 can go into either 10 or into 4. It doesn't matter which one we do, it's going to end up being this, we'll get the same answer. So, you know, maybe I make the 2 go into 10 to give 5. And then this 6 and that 4 both have a 2 in them. So this becomes a 3 and that becomes a 2. So I end up with 3/10. I agree with y'all. I too got 3/10. Good job. I was just a little slower getting there than y'all were. Perfect. All right, how are we feeling about this? I'm going to do one more, just because I have time. One last one, and this time I really will use different colors. All right, let me put up one more problem. So, suppose that a local breeder, a local dog breeder, suppose that a local breeders 10 newborn puppies Mr. Simpson stole my other marker board, so now I only have the one marker board. Actually, it was his to begin with, but he stole it from me anyway. So now I'm having to rewrite this. Otherwise, I could have picked up that marker board and put it here. Mr. Simpson. Okay, so back to this. Newborn puppies has a genetic defect that will appear later in life. Due to the high expense, the breeder doesn't test all of them. The breeder chooses only 3 to test. Suppose that one of the local breeders' 10 newborn puppies has a genetic. Oh, I didn't write that right. Suppose that one of, I need those 2 words in there. Suppose that one of a local breeder's 10 newborn puppies has a genetic defect that will appear later in life. Due to high expense, the breeder chooses only 3 to test. So they're testing for this thing, but then what? Oh, then I want to know what's the probability the breeder gets that test, or the breeder, what's the probability the breeder I don't know what I'm doing. Darn it. What's the probability the breeder chooses, or the breeder, help me finish this, Mr. Simpson. I didn't write down the question, and so now I'm lost. What is the probability the breeder, suppose the local breeder's 10 newborn puppies has a genetic defect that will appear later in life. Due to the high expense, the breeder chooses only 3 to test. What am I looking for? I want to know the probability the breeder, you can't read the board? Me neither. Suppose that one of a local breeder's 10 newborn puppies, is it blurry like for all of y'all, or is it blurry, or is it just, I want to know about the camera here. Is it really blurry, or is it just I wrote this one poorly? I'm trying to work on the camera of this thing. Due to the high expense, the breeder chooses only 3 to test. What is the probability the breeder chooses the one with the defect? I don't know why I was having trouble with that, with the defect. There, I did it. Oh man, that was hard. Yeah, y'all tell me, is it clear or not clear? Is this blurry or not blurry? Okay, good. Okay, good. Okay, good. All right, so it's just his old eyes. Good. Okay, good. Okay, now, I don't know why I was struggling with that. There's our question. Now, what is the population here? It's very blurry on the ends. Okay. Good to know. I need to know that. What's my population here? I like it. 10 puppies. How many of those 10 puppies am I choosing? So what's my sample size? 3? Good. What is the successes? What's the total number of successes? Three. Yeah, 3 is my sample size, and then just 1. Good. And then how many of those am I going to choose? Also just 1. Okay, so I'm going to fill in so that the probability of success is equal to, well, on the bottom, I'm going to put my total. So on bottom, I'm going to do 10 choose 3. Total population and the sample size I'm choosing. Then I'm going to do my number of successes, which I only have one with that genetic mutation, and I want to see, am I going to choose that one in here? Good, 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 good. Y'all got this. And then, how many are left over that don't have it? Well, that means that 9 of them don't have it. And how many of those 9 would I have to do? Because there's one with the genetic defect. And then we want to choose that one. So it is 1, choose 1 there. Oops, that's not right. So the ones that are left then are the 2. Notice that has to add to here, and that has to add to there. I fell apart on this last question. I don't know where my brain went. We got this though. Okay, so 10 choose 3. 10 factorial over 10 minus 3 factorial, and that 3 factorial. What is 1 choose 1? Then 9 choose 2, well I have to actually write that one out. So I've got 9 minus 2 on bottom, 2 on bottom, and then on top I've got that 9 factorial. Okay, that 1, I don't even care about him anymore. Maybe I'm using to help me with the... Then here I'm going to stop at 7 and stop at 7 on both of them. So here I'm stopping at 7. That I'm going to count out. 3 times 2 times 1. 10 times 9 times 8 times 7. Here, I'm going to stop at 7. 2 times 1. And then this I'm going to stop. 8, 7. So, boom, boom. Boom, boom. This 2 goes into that 8 4 times. So all I'm left with there is 9 times 4. On bottom, that 8 divided by 2 is 4. Or maybe you did it into the 10. It's okay, you can do it there and it's going to be the same. And then this 3 goes into that 9 3 times. So you may have 5 times 3 times 8, whereas I have 10 times 3 times 4. We're going to get the same answer in the end. It doesn't matter. Those are going to multiply to be the same. So here I have 10 times 3 times 4. Now, this on top and that on bottom. This divided by that gives me 3, and I just end up with 3 out of the 10. 3 tenths. So, what do you think? That's what you got too? Perfect. Fantabulous. Wonderful. This kind of reminds me of that poison pill one, because the probability I get it is 1/10 on the first try. Or I could not get it and get it, so the probability I end up doing that. Remember that poison pill one? So I either choose the puppy on the first one and I'm done, or I get the not the puppy with the 1 and the puppy, or it's not puppy, not puppy. I end up with that 1/10. So we could have done it with the classical that way, but this way works too. All right, what do you think? Hypergeometric, not so bad? Your job, if you haven't finished the binomial, go get that binomial done first and then upload it. So that if something happens and you upload it wrong or you have some mistakes in there somehow, then I can correct it and you can turn it back in. And then do your hypergeometric. I'm going to be right here on Discord pretty much all day. So come join me on Discord, except for maybe when I plant those 2 trees. I'm going to be on Discord, so come join me, get that done, and then go ahead and upload it too. And then tomorrow I'll come to the task, whatever the task is for this week. Got it? Get it? Got it? Stay away. Good. I'll be on here in just a second, Adam. I'll help you with number 9. All right, guys. Whew. Math made simple. It's Simpson Math. Thanks for watching. Happy April Fool's Day.